Okay, welcome. So in this video, we're going to be covering the main structures of topology, which are open sets, closures, boundaries, and interiors. You'll generally be working with closures and open sets because they're just the most useful. If you're doing touching, closures are add everything the set's touching, so it's the most intuitive way to work with touching. And if you're doing approximation, open sets are the accuracies in your space. So open sets are the easiest to work with in that case. So what we'll be doing is showing that if you define any one of these structures, you define all of them. So if I define open sets, I can use that to define closed sets, which I can use to define closures, which I can use to define boundaries, which I can use to define interiors, and then I can redefine open sets and I'll get the same thing back, the same open sets back. Um, So you may notice how this is a circle and circular logic is bad. So what we do to get around this is these arrows, these going from one to another are the induced definitions. So instead of defining the induced definitions, we plant one of them. So like we say we define the open sets with their defining properties, their axioms, and then we'd move on to define we'd use the induced definitions to define the rest. We'd and then we'd redefine the open sets and we would get the same open sets back. You won't get this like ascending spiral thing. That'd be really confusing. You just get a circle. It just you redefine the same open sets when you induce them from this big circle. And that's what we prove down here. I'm not going to be going through the proofs in this paper. I'm just sort of going to be touristing it. If you want to read the paper, I'm just going to introduce you to notation that you might not be used to, especially since it's not super intuitive. But I will be going through the conclusion because this has a lot of value. It's like all of the things that you should take away from the paper. So I mean, this video will be the takeaways from the paper. So the first thing I'll get into is like how do we actually define a topology? Like what does this mean? What are open sets? Where do they live? What is a closure? Where does it live? So this is saying that open sets, the topology, this T is the topology. It's the collection of open sets. So if I write A is in T, that's the same thing as saying A is open. Uh, this is saying that the P of X is the power set of X, which is the set of subsets of X. So it's saying that every open set in X is a subset of X, which hopefully makes sense. If you're doing a topology in the real numbers, you're not going to have a complex number in one of your sets. That just doesn't make sense. So next is closed sets, and it's written with A and T star. This is the same thing as saying A is closed. A and T star means A is closed. Okay. And then instead of being a collection of sets, the closure, boundary, and interior are functions. They map from subsets to subsets. So they take subsets in the space and give you another subset in the space. An example would be the open interval from 0 to 1 under the closure maps to the closed interval from 0 to 1. Just a simple example there. So next is I guess this notation right here is saying that a closure is written with as A with a bar over it. There's like parentheses with a dot is just like a placeholder for it. So the same thing with the interior. The interior is written A to the circled power, which is a bit weird, but it's become common. And then this boundary is just a normal function. It is partial of A. It is written with the partial derivative symbol because outside of topology, you are talking about boundaries when you're talking about boundary conditions of partial differential equations. It's just sort of the where it's useful, so it's what the notation became. I don't really know the history of that, but it sort of makes sense. I've never talked about boundaries outside of partial differential equations in topology. And in partial differential equations, it is only boundary conditions. Okay, now we're going to cover the defining properties of open sets, which are I covered in my mug donut video, and I'm not going to cover them in much detail here, especially because these two sort of require a story. So go watch that video if you haven't seen it, and I'll explain the defining properties there. So they are that the full set is open. So if the open sets contain nothing the outside touches, the full set nothing is outside of it and nothing touches nothing, so nothing is touching the outside of or the outside isn't touching the set at all. That's sort of the idea. That's why it's open. I'll explain that one. These two, go watch the other video. I'll explain them, but I won't explain why they're true of open sets. So unions of open sets are open. That's what this is saying. If you have a bunch of open sets and you take all of the things that are in one of those open sets, it will be open. And then intersections of two open sets are open. If you have two things that are open and you take all of the things in both of them, that will also be open. So yeah, closed sets are sort of the mirror image of open sets. Instead of the full set is open, it's the empty set is closed. Instead of intersections of open sets are open, it is, or sorry, instead of unions of open sets are open, it is intersections of closed sets are closed. And instead of intersections of two open sets are open, it's unions of two closed sets are closed. So you replace full with null, you replace union and intersect, you swap unions and intersections. That's sort of the idea there. So the closure I also covered in my mug donut video. The basic idea is that the closure adds everything the set is touching. That's the closed sets are everything or like contain everything they touch. That if like you look at the interval from 0 to 1, there's nothing outside of this that like gets touched. Like 0.0, you can get as close as you want. You could get like 1.000000001, does not matter, and it does not touch this set because there's some distance between them. Okay. And then the open set does not have that same idea. The open set from 0 to 1 is touching 1, even though it's outside of 1, so it's not open or not closed. It is open. Uh, I guess it's worth noting that you can have sets that are not open and not closed. Like the full set is never open or closed. Or sorry, the full set is always open and closed. So is the empty set. It's always open and closed. We'll show that later. And you can have sets that are like not open or closed. Like every half interval is not open or closed. Yeah, that's not open or closed. Okay, back to the closure. It adds everything the set's touching. So nothing touches nothing, so the closure of the empty set is empty. Hopefully that makes sense. Since it's only adding points, sets are in their closures. It's only adding points. Hopefully that makes sense. The closure of the closure is itself. So if you do the closure twice, it's the same thing as doing the closure once. This is basically saying that closures contain everything they touch. Closures are closed. That is what it is basically saying. And then it is saying that closures of binary unions are in the unions of closures. It is if it's touching one of them, it's touching one of them. That's kind of trivial. If it's touching A or B, it's touching A or it's touching B. There, slightly less trivial. Okay. Next, I'm gonna skip over boundaries for a second and go to the interior. The interior is very similar to the closure. It's instead of the empty set, it's the full set. The full set is its own interior instead of the empty set is its own closure. The empty set is removing everything the outside touches, so it's only removing points, so it's smaller. Similar to how the closure of the closure is itself, the interior of the interior is itself. That's basically saying interiors are open. And then interiors of binary intersections are the intersection of interiors. So, not as easy as to describe as this closures binary unions thing. That's pretty intuitive, I think. I don't know how to explain this intuitively. It's sort of just the flip side of the closure one. And then lastly, we have boundaries, and boundaries are obnoxious. We hate boundaries. We only deal with them when we need to. We're never going to define a topology with a boundary. I just kind of showed you did in this, or you can in this paper for fun. You're actually never going to define a topology with anything but a closure and open sets, and 90% of the time it is going to be open sets. It's like 90% open sets, 10% closures, never closed sets, boundaries, or interiors. But you can if you wanted to, I guess. Um, okay. So, the null set or the boundary is the stuff touching the inside and outside of the set. So if I have the interval from 0 to 1, 0 and 1 are the boundary because they are touching the outside and are in the inside, so they're touching the inside. So the null set has no boundary. Nothing touches nothing, so nothing can touch the inside and outside of nothing. Hopefully that makes sense. Sets share a boundary with their complement. I don't even know how to make this not make like okay. So it's the boundary. It's got to be the stuff touching the inside and outside. So it's also touching the outside and inside. Hopefully you get that because I don't know how to explain it better than that. And then boundaries contain their boundaries. Containing your boundary means you are closed. So this is saying boundaries are closed. Not really intuitive, but it is one of the defining properties of boundaries. And then boundaries of binary unions are in the union of the boundaries. I am going to draw a picture for this because this is quite confusing to understand, but if I draw a Venn diagram, it's not. So that's our first set. We have two sets that are basically intersecting circles. So A would be this first circle, and then B would be the second circle, and they intersect in the middle. And so I just drew what I drew, or I guess the set would be the inside of these circles, and I just drew the boundaries of the circle. So what I just drew is the union of the boundaries, because I just drew the boundaries of both of them. If I wanted to draw the union or the boundary of the union, I would not draw these inner spots since they are not touching the outside. These ones go. These two like lines go. It's a subset of the union of the boundaries. Hopefully that makes sense. Another example would be like if I have the interval from 0 to 2 and then I union that with the interval from 1 to 3. The union of the boundaries would be 0, 2, 1, and 3. But then if I do the union first, I get the interval from 0 to 3, and then the boundary is just 0 and 3. So it's still the union of the boundaries is a subset of the boundary of the union. That's two examples of that being true. And it's true in any topology, of course. It's one of the defining properties. And then the last one is that the boundaries of smaller sets are in the larger set or its boundary. So if I draw like a picture for this, imagine this is our bigger set, and then I have a smaller set sort of here. They share a boundary here, so this would be a case when the boundary of A is in the boundary of B, and right here, the boundary of A is in the boundary of, or is in B instead of the boundary of B. And moving on to the induced definitions. Okay, so the induced definitions is sort of it's how we do this circle. We planted one of them with the defining properties, and then the induced definitions sort of move from open sets to closures to boundaries to interiors, and then back to open sets. And if it is true, like if you have the defining properties of the induced definitions have the defining properties. Basically, like when you induce closed sets, they'll have the defining properties of closed sets. Proved in this paper, not going to cover those proofs in detail. You can go read the paper if you want. It's in the description. So the first is the closed sets. So the open sets contain nothing the outside touches. So you draw it like with a dashed boundary because it doesn't contain the boundary, and the open interval from 0 to 1 does not contain 0 and 1. So if it doesn't contain anything the outside touches, it doesn't contain the boundary. So that means the outside of an open set has to contain the entire boundary. Hopefully that makes sense. And if it contains the entire boundary, it's closed. So the outside of an open set is closed. That is what this is saying. Um, where you can read it by saying, okay, this is all of the stuff in the power set, all of the subsets of X, and then this restricts it to specifically the ones whose outsides are open, whose complements are open. Okay, so that is closed sets. And then defining the closure with closed sets is probably the most complicated. It's certainly the most complicated. And it is the intersection of all of the closed sets containing A. So why is that? The closure is the smallest closed set containing A, and this happens to fulfill that. So it's the smallest closed set because it's smaller than every closed set. It it uh it is the intersection of all the closed sets containing A. So every closed set containing A is in the intersection, and intersections can only make things smaller since it's like taking away points. And then the it contains A because every set in the intersection contains A. So it's the smallest closed set containing A. And then lastly, it's closed because it is an intersection of closed sets. We assumed in the defining properties of closed sets that intersections of closed sets are closed. So since it's an intersection of closed sets, it's closed. It is the smallest closed set containing A. Okay. Yes. So here is the boundary. This one's one of the more simple ones. The boundary is everything the inside and outside touches. So this is everything the inside touches, and this is everything the outside touches. Sort of the closure adds everything the outside touches. So hopefully that makes sense. And then next is the interior, and it removes everything the outside is touching, and the boundary is the stuff. Everything in A the outside touches is in the boundary. So if you remove the boundary, you remove everything the outside touches, and you get the interior. And lastly, for open sets from the interior, again, the interior removes everything the outside touches. Open sets contain nothing the outside touches. So if your interior is your set, it means you removed everything the outside touches and you didn't remove everything, or you didn't remove anything. So you don't contain anything the outside touches, which means it's open. So it's saying all of the sets that are equal to their interior are open. Okay. And then from here, we sort of get down to the proofs. I will not be covering these in detail, but I will be covering the lemmas. This one doesn't have any lemma. It's just sort of applying De Morgan's law. It's pretty simple if you've dealt with set theory before. This one is a bit more confusing. It has three lemmas. We need to show that the closure of any set is closed. So that we sort of explained that it's this intersection is the smallest closed set containing A. So it contains A from K2. It is closed from CK1, and it is smaller than every closed set containing A from CK3. And then CK2 is just sort of how you would define closed sets from closures. So it's one of the core important ideas. A set is closed if and only if it is equal to its closure. Sort of like how interiors are defined or open sets are defined if they're equal to their interior. Closed sets are defined if they're equal to their closure. Of course, you could we did the circle in one direction, but you could totally do the circle in the other direction. There's no reason why you wouldn't be able to. And these theorems, these definitions that show up if you go the other direction tend to be very important for the theorems going in the direction you're going, if that makes sense. Okay. So next is defining the boundary with the closure. So, this is probably the most annoying one. It might be I don't know. Boundaries are obnoxious. They're consistently obnoxious. We hate boundaries. Uh, the main lemmas that we need to prove, some of these don't even involve the boundary. This one is saying bigger sets have bigger closures. So it is, hopefully that makes sense. It's adding everything it's touching. So if it's touching, or if it has more, then it's touching more. That's sort of the idea. This one is that the closure of the closure is its bound, or the closure of the boundary is the boundary. If something's equal to the closure, it is closed. So this is saying boundary is closed, which which is the what is that's also what B3 is saying. So it's sort of why that comes up. It's yeah. And then the next one is sets contain the complement of the closure of their complement. The complement of the closure of the complement, this is the interior. So this is saying the interior is contained within A. Um, this is, again, this is I2, I believe. This is one of the defining properties of interiors. They're contained within the set. It is only removing points. This is just saying the same thing, but in terms of defining the interior with closures. So, yeah. And then this one is how you would define the closure using the boundary. You just add everything that's in the boundary. That is what that proof is. Um, and you would need all of these, since the boundary is so complicated, you need all of these like ways of translating between the closure and the boundary and such. Yeah. And then, of course, proofs in the description if you want to actually read through this. It's a bit obnoxious. It's probably a better use of your time to try to do it yourself. Try to do the proofs yourself instead of trying to like understand the proofs that I wrote. Okay, so now we have the defining the interior with the boundary. Of course, we just removed the boundary, but we have a few lemmas that we need to do to work up to that. This is actually a typo that I noticed while recording. This equality is supposed to be a subset. It says right here that the boundary of the interior is in the boundary, not that the boundary of the interior is the boundary. It's supposed to be a subset, not a set. An example would be the rational numbers uh, in the real numbers. The interior of the rational numbers is empty, and the empty set does not have a boundary, but the rationals do have a boundary. The rationals, their boundary of the rationals is the entire real numbers. So, yeah, it's a subset, not necessarily equal. And then bigger sets have bigger interiors. Uh, Again, I hope this makes sense. If you're removing everything the outside touches and the outside contains less because the set's bigger, like it's gonna it's going to add more points. It's going to have more points. Hopefully that makes sense. So, yeah, that is boundary from interior. And then next we have defining open sets. Actually, last we have defining open sets with interiors. So again, it's open if it's equal to its interior, and our lemmas are these. This is saying that the interior is the largest open subset. It's the largest open subset contained within A. So that's sort of what this is saying, similarly to how the closed set or the closure is the smallest closed set containing A. The interior is the largest open set containing A. Or yeah, I think I said that right. So hopefully that if it's open, B is open and B is contained within A, then B is contained within the interior of A. And then the interior of A is the union of all the open subsets of A. It's sort of saying the same thing. It's just saying the interior is the so this is all of the open subsets of A. It's the intersection of the power set of A, so subsets of A, with the topology, so the open subsets of A. The union of all of those is the interior because the interior is the biggest open subset of A. Or the biggest up open, yeah, I think I said that right. The interior is the biggest open subset of A. Yes. Okay. And then we have the structural uniqueness ones. This is showing that the induced definition of open sets defines open sets. So we put a hat over T and then prove that it is equal to T. And then this is the induced definition of the boundary. So, or of open sets using the interior. I don't know where boundary came from. So here we prove that the interior is the complement of the closure of the complement. That is what this one is. Uh, yeah, it's you can go through the proof if you want, but we talked about this earlier. This is how you would define the interior using the closure. So I figure I should actually explain why the interior is the complement of the closure of the complement. The interior removes everything the outside touches. So everything the outside touches would be the outside is this is the complement. Everything the outside touches would be the closure of the complement. And so removing everything the outside touches would be everything that does not uh, touch the outside, or the outside does not. It's the complement of the closure of the complement. Hopefully that helps clear things up a little bit. Um, so, and then we use that lemma to go from defining the previous open sets to the new open sets and showing that they're equal by showing they're subsets of each other. Okay. And then again, the induced definition of closures, just put a hat over it and then show it's equal. And we don't even need to prove any lemmas for this. It's pretty direct. And then the induced closure, again, we just put a hat over it. I'm liking hats. And we showed that the closure is it's sort of how the interior is the complement of the closure of the complement. The closure is the interior, or the closure is the complement of the interior of the complement. Yeah. Okay. And then the induced boundary is the original boundary. This has this little theorem, which is basically saying that the closure is the union of the boundary and itself. It's saying we had this previously proven, and we just basically take the complement of the A and then the replace it using replace the complement of A with the complement, or the closure of the complement with the interior of the complement, which we can do from up here by taking the complement of both sides. We get that the closure, I guess this isn't the exact one, but the other one, yeah. If we, I guess, if we take, where is that theorem? Okay, here it is. It's this theorem. It is, we take the complement of both sides and we get that the interior's complement is the closure is the complement of, or the closure of the complement. The complement of the interior is the closure of the complement. We just take complement of both sides and we get that. Um okay. So from here we go back. We just use that basically on a complement. It's a bit confusing, but that is how we get this one. It's a very roundabout way of saying it, but we need it for the proof. And then for the induced interior is the original interior. Instead of just putting a hat over it like I have been doing, I filled it in because this little dot thing with a hat over it is pretty hard to see. So I just filled in the circle for the induced interior. And we don't even require any lemmas. This is pretty direct. We use the lemmas we previously proved. We have IK1 to go from interior to closure, and then we have KI1 to go from closure to interior. We just do that. Okay. And then for the conclusion, we have the main relationships between, these are like sort of the main takeaways, the most important things. Um, there's like a billion ways to say A is open, and this covers them. If A is open, then A complement is closed. These are all equivalent. So A is open is equivalent to A complement is closed, which is equivalent to A is its own interior, which is equivalent to A contains none of its boundary. So those are the four different ways you can show that, or you can say something's open. I've been using them sort of periodically throughout when describing things intuitively, but this would be where this is actually proven. So boop, there is, this is those proofs. Then closed sets, A is closed is the same as A complement is open, is the same as A is its own closure, is the same as A contains its entire boundary. And that is where this proof is. These proofs are right here. For this one, we should prove these small relationships with closures. Or, well, we already have proven them. It's that A is the closure is the union of a set with its boundary. So you add the boundary to a set and you get its closure. And then we already proved that the closure of the complement is the complement of the closure or whatever, or the closure is the complement of the interior of the complement. I hate this one. It's useful sometimes, but it's obnoxious regardless. And then we have a bunch of different ways of saying that X is in the closure. So obviously, if it's in the closure, it's in the closure. If it's in every closed set containing the set, it's in the closure of that set. And if it's every open set containing a point in A contains the set. This is actually one of the most important ones. If every open set containing a point has a point in A, then it's in the closure of A. This is saying that the closure adds everything that you can approximate to any accuracy with A. It's insanely important. If so, we would take an accuracy of A, an open set, or sorry, we would take an accuracy of X, an open set containing X, and then we'd find this Y that is in A and in that accuracy. So it's a point in within the accuracy that is in A. So A can approximate X to any accuracy. We often say that neighborhoods are the open sets containing a point. So like a neighborhood of X would be an open set containing X. So every neighborhood of X contains a point in A. Every accuracy of X contains an approximation in of X to that accuracy in A. Um, Hopefully that makes sense. And then I have the proof down here. Okay. And then the interior, similarly, you see there's only two equivalent definitions instead of the three for the closure. I don't know if there's a third one that I'm missing for the interior that it makes any sense, but this is what I've found that well, the interior is what happens if you remove the boundary, and then that the interior is the complement of the closure of the complement. Those are two different ways to write the interior. And then X is in the interior if there is some open subset of A containing X. So if there's a bit of, since the interior is the biggest open set containing X, if there's an open subset containing X, the interior is bigger than that, so it also contains X, and X is in the interior. Okay. And then lastly, we have the boundary. And the boundary is the intersection of the closure with the closure of the complement. That's from the definition. And the boundary is also the closure without the interior. So if you consider the closed set from 0 to 1 and then remove the open set from 0 to 1, you just get 0 and 1, which are the boundary. Okay. And yeah, that I proved that right here. And then finally, we have this idea of an isolated set. So a set is isolated when it is open and closed. If it's open, then the outside does not touch it. And if it is closed, then it contains everything it touches, so it doesn't touch the outside. So it's isolated if the outside isn't touching it and if it isn't touching the outside. So if it's sort of an island, like if this is our space, the stuff inside of these two things is our space, then each of these is going to be isolated. But if I take like some part of it, then it is not isolated. The only two isolated sets in the real numbers are the empty and the full set, and actually the empty and the full set are always isolated, which I prove here. And also if an isolated set, a set is isolated if and only if it has an empty boundary. So if it doesn't share a boundary with anything, then it is isolated. That is sort of the concept there. And then finally, isolated sets have isolated complements. So if it's isolated, then its outside is also isolated. So hopefully that makes sense. And this concept is very useful for thinking about connected sets. Specifically, a set is connected if, like the real numbers, the only isolated sets are empty or full. So that is about it. If you like this video, this is probably the worst of the videos that I'm gonna get on my channel, so subscribe and it'll only go up from here. So see you guys next time.